First, I will start with a background about the problem, then the current solutions. Then I will talk about the scope of the problem, formalize it. Then I continue with the proposed framework. Then I'll move to the validation, present some results. And finally, I will discuss the future direction and conclude the presentation. Well, the global prevalence of diabetes among adults almost doubled in 34 years, from less than 5% to 8.5%. And recently, an estimated 1.6 million deaths were directly caused by diabetes. And the table shows a recent statistic report from World Health Organization, and about 9% of US adults have diabetes, 70% are suffering from being overweight, and 35% are dealing with obesity. And these chronic and widespread diseases require patients to monitor their food intake. Food journaling, where patients keep track of their food intake, is currently the most common method for doing so. However, food journaling is subject to self-bias, it recalls errors, and also fully adhered by the patients. Well, three main aspects of food intake monitoring are when the eating takes place, what is eaten, and how much is eaten. And to answer these questions, a nutritionist typically rely on self-reports. While these tools suffer from several limitations, bootstrapping the user with semi-automated tracking of how often, at what time, and for how long they ate holds significant promise in this case. For example, like step trackers and step counting applications, where just a course of estimate of the activity levels can motivate the users to improve their activeness and behavior. Also, monitoring the food intake can perhaps help in modifying and improving their unhealthy habits. And the age of wearable is upon us, and wearable devices are growing in popularity at a tremendous rate. And fueled by pervasive nature of these new technologies, the interest in automatic food intake monitoring is increasing. The automatic health monitoring systems can help with monitoring eating habits. They can assist users who need to follow a special dietary plan. They can accommodate users with special health conditions such as diabetes. Also, patients who are admitted to take their medication at a certain time of the day, for example, after or between a meal. And over the last decade, a significant amount of research has explored various approaches to fully automate food intake monitoring. They used a wide variety of sensing approaches for this purpose. For example, using multiple on-body sensors, we expect it to be more robust than using only a single sensor. If these multiple sensors are combined in a way that each of them provides unique information toward the goal of dietary monitoring. However, using multiple sensors is not socially accepted and not convenient for the user. On the other hand, there are specialized devices that are invented only for food intake monitoring, but they are not convenient and widely used by the end user. So these state-of-the-art and recent approaches seem to be impractical for everyday usage. To address this issue, the goal of this research paper was to develop a machine learning model that uses a smartwatch as an easy-to-use and prevalent device for eating moment detection. First, let's see some of the challenges of proposing such a model using a smartwatch. For example, we cannot rely on a model that is trained from data that's collected from one or few subjects in the lab setting to be generalizing to real life scenarios. For example, during our data collection sessions, we observe that people perform the same activity differently. Even a specific user patterns in performing the activities in real life scenarios or comparing to the lab setting was different. Therefore, to have a robust model, we need to retrain the model for the new users or the new setting. And retraining the model needs a large amount of labeled data, and collecting and labeling data is a very intensive, labor-intensive, expensive, and time-consuming process. Also, another challenge is how to collect the ground truth labels in the real-life scenarios. One solution could be very body-worn cameras and collect video or frequent pictures to add labels to the sensor data, which imposes serious privacy concerns. So to address these challenges, we propose proximity-based active learning on stream data in short paths, which since it's attainable to collect a large pool of unlabeled data, but the labeling process is itself expensive, in paths we try to leverage the unlabeled data. So we use a semi-supervised learning model to construct the efficient model while choosing just a small subset of unlabeled instances. And those unlabeled instances, we ask an expert or user and query for the labels for those unlabeled instances. And active learning is potentially a feasible approach to query sensor data. So we can iteratively choose among the most informative instances, ask the expert to label them, and add them to the model to improve the performance. But one serious constraint here is that the sensor data is sampled in real time, and decision about either querying or just skipping a data segment needs to be done in real time. I move to the problem statement. Well, we formally define the problem that PALS is trying to solve. We call it limited budget training, in short LBT. And to define this problem, first we consider we have this expert that can label the sensor data by either remembering what happened, by either remembering the activities or watching a video that was recorded from the activities. This labeling expert allows us to develop a basic pool-based active learning algorithm that selects the most informative instances from a large pool of unlabeled sensor data. And the goal here is to efficiently construct that training data set using the selected instances and the already labeled instances, that the classification error is minimized. So to find those most informative instances, we design an instance selector function, as you can see in this slide. This instance selector function selects the instances to fit to the training process. And the instance selector function decides if an instance is informative enough to be added to the training set by considering the budget limit. For example, the budget tells us we only can query 100 instances from the instance pool. This instance selector function, as you can see in the formulation, we minimize the amount of misclassification, which is computed by the predicted label by the function f, difference between the predicted label and the actual label, if the instance is selected, and considering the budget limit. So only 100 samples, for example, based on budget can be selected. Well, this LBT has a major limitation, and the problem that it assumes the user or the expert has a perfect memory retention. So in mobile health technologies, they monitor end user continuously, and user might not remember the past events. So in the next slides, I formally define the problem of training with limited budget on a stream of data. Here is the problem formulation for the limited budget training on data stream, or in short, LBTS, which is defined as efficiently deciding whether to query the true label for the instance at timestamp T. And when we have the label, update the classifier as the label becomes available in real time, such that the classification error is minimized, again, like the non-stream version. So if you look at the slide, we assume X is a sequence of sensor instances that are being produced during time frames 1, 2, and so on. And here the objective function aims to minimize the amount of misclassification error considering the budget constraint. And the difference here is the function f of t, the prediction function that is specific to the timestamp. It shows the classification function as at timestamp t. Well, here I'll talk about the modeling of the paths. So we got inspired by the graph-based semi-supervised learning research, and we proposed to construct a proximity-based model to quantify similarity between the data instances. And the intuition behind the proximity modeling and label inference is smoothness assumption. What does a smoothness assumption says? It suggests that the instances that are close in feature space should have the same or similar labels. The process of building the proximity-based model includes 2 phases. In the first phase, we build a proximity graph on both unlabeled and labeled instances, as you can see in the left side of the slide. Then the reason that we also include unlabeled data is that in absence of enough labeled training data, we want to leverage unlabeled data that and potentially improve the performance of the final model. And each node in this proximity-based graph is an instance, and edges shows the similarity between a pair of the instances. And we use Euclidean distance to compute this similarity in feature space. Then in the second phase, which is label inference, it focuses on generating labels for the unlabeled instances, and through an iterative label propagation method. As I mentioned, we use Euclidean distance to compute the similarity between the instances. And to also avoid the confusion of the instances that are far from each other, this similarity-based graph uses k-nearest neighboring schema. So we just connect each instance to only k-nearest neighbors of that other instance, and the edges are computed. The value on the edges are the Euclidean similarity between the instances. The reason we chose k-nearest neighboring is that it's one of the most similar approaches in semantic graph construction. It works well with our data. This slide shows the framework of the offline version of the paths. So initially, we have, among all the recorded activities that we have, there is no or just small set of labeled instances, as I mentioned. but we have a large pool of unlabeled instances, as you can see in the figure. The algorithm first constructs a proximity-based graph on both unlabeled and labeled instances, the entire data set. And in the next step, during several iterations of active learning, the instance selector searches through the unlabeled instances, finds the most informative instances, then asks the expert to provide label for them. For example, we select a bunch of instances like x1 to xk, given the constraint that we have. For example, at most, we can query for k instances. From all the unlabeled instances, we select the most informative instances, k of them, ask the expert to label them. Once we have the label, we add them to the labeled dataset and update the model. And here is the algorithm of offline version of the PAL. As I mentioned, the procedure starts with building the model using labeled and unlabeled data. Then in every iteration of the active learning, it starts from line 3. After we build the model in line 2, we use the model to compute the information gain of the unlabeled instances. Then based on the budget, we select the instances with the highest information gain, add them to the labeled small set of labeled data that we had, and update the model. Here is the real-time version of the PAS, the framework of the real-time version of the PAS, which works with stream-based data, stream data. So real-time PAS assumes that the user can provide labels only for the current or very recent activities. So in this approach, each instance is evaluated once, and as a result of this evaluation, the instance is either discarded from the further analysis or is used to query from the user for its label. And if the system receives a label from the user, the next step is to update the model with the new instance to make a more personalized model. Here we have a certainty evaluator, which is similar to instance selector function. It evaluates the current model's certainty in classifying the instance at timestamp t. And then after evaluating the certainty of the instance, we compare the entropy of that instance with a information threshold, or lambda. Here we show it with lambda. This information threshold, I will talk about it more later, but if it's more than if the entropy of that instance is more than that threshold, we select that instance, ask the user for the label, then add it to the model and update the model with the new instance. Here is the algorithm of the real-time PAS. So it uses the first, as I mentioned, uses the current model to evaluate the instance at timestamp t. As you can see, lines 2 and 3, it makes a prediction of the instance using the model that we have currently. Then we calculate the entropy based on that prediction. And if the entropy of that instance is more than the threshold that we computed, then it asks the expert for the label and updates the model with the labeled instance. Otherwise, it doesn't do. Also, we consider the budget here. Delta shows the budget. So just query as much as the budget. Well, about the information threshold, we need an algorithm to adjust the value of informative threshold to balance labeling over the instance space. And to obtain an effective performance, the algorithm needs to avoid both very high and very low values of lambda. And the reason for that is that high values will translate into highly conservative approach, where only a small number of questions are asked from the expert. Therefore, the algorithm can fail in personalizing the model for the current user. On the other hand, for very low values of lambda, these values will result in the algorithm that exhausts the budget very fast. Therefore, the algorithm loses the probability of sampling over the instances space and might lose informative instances in the future. Therefore, we need to have an adaptive algorithm to adjust the value of the lambda to create a balance between the time and budget. Here, how we balance this lambda value, as you can see in the figure, we have the lambda of t, delta of t shows the budget that we have. So we compute delta for each timestamp based on the formulation as the fraction of the whole duration of the active learning process and the initial budget. So the capital T shows the whole duration of the active learning process, and T shows that the specific timestamp. Then we have a set of entropies. That these entropies are sorted in a list. So, for example, entropy 1 shows the entropy that only one instance from those one instance has higher entropy than entropy 1, and entropy of delta T shows that a specific entropy that delta T of the instances have a higher entropy than the E delta T. So in each step, we go through this list and find the entropy. For example, we have six remaining instances from the budget. For example, the initial budget was 20. We already selected 14 instances. We only have 6 remainings. We go into the list and find the entropy that we know that only 6 instances are higher than, have the entropy higher than the entropy of the selected entropy. We select that one, set it as the adaptive lambda value. So I move on to the validation. First, I'll check if anyone has any questions about the, oh. I hope, I mean, I just read the comment about the mic is a little low. I hope that that wasn't a very important issue and everybody could hear me. So I move on to the validation now. I try to speak louder. Well, to validate PALs, we designed an experiment to collect rebel motion sensor data during eating sessions. The data set that we collected contains 20 sessions of eating data collected with 4 different participants. Each data collection session lasts about 20 minutes, and participants were continuously video recorded. In data collection sessions, participants were asked to wear a Samsung watch on their dominant hand, and the participants were asked to eat a meal while performing other related activities such as drinking, eating, talking, working with laptop and texting. The data set contains 32% eating activity, and the rest were non-eating. Oh, okay. So we also, so this data set is publicly available. We also validated the method on 2 other data sets similar. We call the first data set SW6S. The second data set, similar data, SW3S, and third data set, SW3W. And the important thing about the third data set that is publicly available is that only 7% of the eating activities were eating. So it's a highly unbalanced data set. Here is the pipeline of the validation. Because I don't have much time, I'll just go through it very fast. We did pre-processing. We filtered the data, remove high frequency noises. We segmented the data to find the start and end of the activities. We extracted 15 features from each axis of the accelerometer and gyroscope sensor data, in general 90 features, and we also did feature selection to improve the power efficiency and also performance of the system. Here is a list of the features we extracted, features that are proven to work well with physical activity recognition, gesture recognition from the sensor data. We also considered some of the things with our data set. Our data set, because it's eating and the duration of the activities in daily life is highly unbalanced. To learn from skewed data, we did upsampling for training process, and for that, for the eating class, we generated synthesized data using a smooth. And performance metrics, we didn't use accuracy because it's misleading for unbalanced data set. We present binary F1 score and recall to compare the performance. And here is the some of the results. First, it's we compared two different similarity kernels to build the graphs, k-nearest neighboring and RBF, and we compared it on SWS3S and SW6S data sets. As you can see, the blue one shows when we use KNN kernel. For the first data set, it was higher. It was similar at beginning iterations. Then by increasing the iteration, it got higher. Second data set was much higher from the beginning. Well, just conclude the presentation because I don't have much time. And well, as I mentioned, the most common approaches, I mean, as I mentioned, use multiple body on sensor specialist devices are impractical for everyday usage. So we propose this machine learning technique that uses smartwatch and off-the-shelf smartwatch to detect food intake monitoring with a limited label data set using active learning. So we leverage the unlabeled data, we use active learning, and with limited budget, we could able to improve the performance of the state of the art and for real life scenarios to detect the eating moments. That's my presentation.